Alright, in this video we're going to prove that the limit as x approaches 0 of sine of x over x is equal to 1. And to do this we're going to use a little bit of geometry. So here on this slide we see some geometric shapes. This is the unit circle, right? So we might call the angle in the unit circle here, call this x, which means that the horizontal edge here in the unit circle has length cosine of x, and the horizontal edge has height sine of x, and the hypotenuse has length 1. Right? And also the edge here, right? This is also the radius of the unit circle. This also has length 1. And what else? Well, the height of this large triangle here, this is tangent x. Okay, so to point out some of the specific sort of geometric figures in here, let's give some of the vertices names. So let's call the origin O. Let's call this point A. Let's call this point Q. And let's call this point P. Okay, and what I want you to notice is that we can look at some of these things like the triangle OAP. Oops. And we also have the circular sector OAP, which is the portion of the unit circle formed by this sort of piece of pie going around the unit circle. Right, so that's circular sector OAP. And finally we have the large triangle, triangle OAQ. And when we compare all three of these, what we see is that the triangle OAP is contained inside the circular sector. So this is a symbol denoting inclusion. And also the circular sector is sitting inside the large triangle OAQ. So most important for us, it means that the area of triangle OAP is smaller than the area of the circular sector, which is smaller than the area of the large triangle. So let's compare those areas. Okay, so the area of the triangle OAP, well, this is a triangle, so the area should be 1/2 base times height. Right? And the base of this triangle has length 1. The height is sine of x. So this means that the area of this triangle is going to be 1/2 times sine of x. Okay, now let's figure out the angle of the circular sector. All right, well, what's the area of the unit circle? Well, it's pi times r squared, and the radius is 1, so it's just pi. But then how much of the unit circle do we have in this circular sector? Well, overall there are 2 pi radians, right, in the entire unit circle, 360 degrees. And how many of those do we have to form the circular sector? Well, we have x of them. That means if we simplify this expression, we get x over 2. So the area of the circular sector is x over 2. And since the circular sector is bigger than the triangle OAP, we can say that 1/2 sine x is less than x over 2. Okay, and finally, what about the big triangle? Right, so the big triangle has base 1. The height is tangent x. So that means the area of this large triangle should be 1/2 tangent x. And since this is bigger than the circular sector, we can say that x over 2 is less than 1/2 tangent x. Now let's take this inequality and let's simplify it a little bit. Okay, so we're going to start with the same inequality, and notice immediately that each term has a 1/2, so we could go ahead and multiply everything by 2. And now let's divide every term by sine of x. So if we do this, we should end up with 1 is less than x over sine of x is less than tangent over sine of x. But tangent sine over cosine, so that means this is 1 over cosine. And now what we should do is take the reciprocal. All right, so take the reciprocal of each term in the inequality, and of course when we do this we're going to have to flip the inequalities. So the reciprocal of 1 is just itself. And this is now greater than the reciprocal of x over sine of x, which is sine of x over x. And this is greater than the reciprocal of 1 over cosine, which is just cosine. And here's where the squeeze theorem comes into play. Why? Well, we want to take the limit of sine of x over x as x approaches 0. So let's take the limit of the larger function and the smaller function as x approaches 0 and see what we get. So the limit as x approaches 0 of the constant function 1, of course, is just 1. And the limit as x approaches 0 of cosine x, well, cosine is continuous, so that means we can just plug in, and cosine of 0 is also equal to 1. So since we took the limit of the smaller function, and that went to 1, and the larger function also went to 1, we can conclude by the squeeze theorem that the limit as x approaches 0 of sine of x over x equals 1. And this is basically a rule that we'll use for the rest of the semester. A slightly more general rule that we'll use is that the limit as x approaches 0 of sine of ax, where a is any number, over ax, well, a is any number at least that's not 0, this limit is also equal to 1. So for instance, the limit as x approaches 0 of sine of 3x over 3x is equal to 1. And the reason this is true, the reason we can use the same formula with a, is because basically we're taking the limit as x approaches 0. And as x approaches 0, if a is any number, then a times x also approaches 0. And so basically we can do a substitution and input the ax, which is going to 0 here. The denominator is also going to 0, and we can use our original rule to convince ourselves that this other rule, the slightly more general rule, is also true and is something that we can use. So the last thing that I'll mention is about this other limit rule involving cosine. The limit as x approaches 0 of 1 minus cosine x over x is equal to 0. And to convince ourselves that we can use this also as a rule, we use the double angle formula, which says that cosine of x is equal to 1 minus 2 times sine squared of x over 2. So basically what we want to do is we want to take our expression 1 minus cosine of x over x and rewrite it using this double angle formula. So we have 1 minus the quantity 1 minus 2 sine squared x over 2 all over x. And notice that the 1's cancel, and so this is equal to negative 2 times sine squared of x over 2 all over x. And now let's flip that 2 so that we see this is equal to negative sine squared of x over 2 all over x over 2. And a more convenient way to write this for us is to write it as minus sine of x over 2 times sine of x over 2 over x over 2. And now what happens is we take the limit of this expression as x goes to 0. Well, this part in the brackets here, this follows this rule where a equals 1/2. So that means this goes to 1. But this other part, negative sine of x over 2, as x approaches 0, well, sine of x over 2 is continuous, so we can just plug in 0, and we see that this goes to 0. So overall, this convinces us that the limit should be 0 times 1, which is 0.